I welcome you all to the next video lecture of EEE 615 Microcontroller Architecture and Organization. In this particular video lecture, we are going to go deep into 8051's architecture. I hope by this time you all are acclimated to understanding the architecture of any controller. I think in today's class we saw about ARM's architecture and different features of architecture. And I also taught you how to interpret the architecture and perceive how the data travels in the architecture. So this is one of the very simplest architecture to start with, 8051. It's very simple and easy to comprehend and interpret. This is the processor, the 8051 actual processor. So if you look at the architecture, it's very evident that it has got 4 ports: port 0, port 1, port 2, and port 3. So there are 4 I/O ports. So you have an inbuilt RAM, an inbuilt ROM, flash memory. So that means since it is flash, it is rewritable. Apart from the 4 I/O ports for interfacing with the real world, it has got timers, counters, interrupts, serial communication ports, special function registers, and even sometimes some of the vendors even add watchdog timers to the architecture. Okay, so if you look at the general features of 8051, I've told this many number of times. It's an 8-bit microcontroller and accumulator based architecture. It's very easy for interfacing with the external world, and the clock frequency or the operation frequency of 8051 can vary anywhere from 12 megahertz to 30 megahertz. It has got a full instruction set. When I say full instruction set, what I mean is it includes multiplication instruction, division instruction as well. Okay, it supports Boolean, which is nothing but logical. It supports several addressing modes like direct, indirect, indexed, and immediate. The 4 ports, what I was talking about, port 0, port 1, port 2, port 3, are all 8-bit ports. As you know, this is an 8-bit architecture, so obviously the ports will be of size 8 bits. So if you look at the external diagram of 8051, or if you look at the pin or the chip of 8051, each port constitutes 8 pins coming out of it for I/O operation. Okay, and all these ports are bidirectional. That is, it can act either as input or output based on how it is being programmed. Okay. So this is a detailed internal architecture of 8051. I'll just give you a few minutes to go through the architecture, look at the architecture, and let us see how much of this you can interpret. Okay, so now if you see, here you have the ALU. Okay, and next to the ALU is what we have is PSW. This is nothing but program status word. So this program status word, you already know, consists of several flags like carry, auxiliary carry, then parity bit, then 2 bits RS0, RS1, and 2 general purpose flag F0, F1. So any operation that happens in the ALU directly affects the indicator flags present in the PSW. So that is why it is associated with ALU. Okay, very close to ALU. Now this is where you have your interrupt, serial port, and timer blocks happening. Now you see the 4 ports: port 0, port 2, and right at the bottom port 1 and port 3. So these are the ports, and again you see the ports are not directly connected to the data bus. In between you have a latch. Each port has its respective latch to hold on to the data temporarily for some time so that the data is not lost. You are already familiar with the DPTR and its functionality. As usual, as you find in any other controller or processor, you have this program counter, you have PC incrementer, okay, then this is program address register, you have your ROM, you have your RAM. Okay, so this is the accumulator A. Generally you type move A comma #5 or whatever it is, right? So this is the accumulator A. This is the second accumulator, or what we call as B register. Okay, both communicate via ALU through a temporary register, so that the ALU performs the operation and the result is stored back to the accumulator. Got it? Now this is the instruction register which carries the instruction that is going to be executed next, and these are some of the IO pins that protrude out of the 8051 for interfacing with real world. This is ground and the supply for the 8051 to get powered up, and this is the oscillator. Oscillator is what provides the clock frequency. This is what can vary from 12 to 30 megahertz. So this is the overall architecture of 8051. Now, if you look at the external structure of 8051, see, the one we see here is the architectural view. The one we saw here is the block diagram view. So this is not actually the architecture. This is the block diagram view, because if you see here, things are very simple. They don't tell you the data path. Whereas if you take this particular diagram, it tells you the data path, how each things flow through 8051. But this particular diagram, if you see, it's the structural diagram that depicts how 8051 will look like. This is the notch which you see in any chip that you buy. So the left hand side of the notch is pin 1. So basically, if you look at it, it's totally a 40 pin IC. Okay, we call this particular kind of construction or structure as dual inline package, or what we call as DIP package. What do we mean by dual inline packages? If you look at this side, the 40 pins are evenly distributed on both sides as 20 pins and 20 pins. Okay, of these 40 pins, some are dedicated for single purpose, like take this example, pin 40 is dedicated for VCC or power supply, and pin 20 is dedicated for ground. Similarly, pin 18 and 19 is dedicated for connecting your clock or the crystal oscillator to the circuit. Likewise, every pin has its own functionality, and certain pins have multiple functionality. Let us see about that in detail now. Let's first take port 1. Okay, what we call as port 1 is from pin 1, okay, to pin 8, all the way till 8 pins, because every port is an 8-bit register, right? So it has got inbuilt. So inside this particular area, you have this latch or 8-bit register which holds the data which comes through this port. So port 1 is from pin 1 to pin 8, and it is single function. It's not multi-purpose. It is simply used as bidirectional IO. It can serve as either as input or output port, or input pins or output pins. That's it. There is no other functionality associated with that. Now let's consider port 3. Port 3 starts from pin 10, because pin 9 is dedicated for reset. Okay, power on reset. It starts from pin 10 to pin 17. Again, these 8 pins. Now this is port 3. This is port 3, pin 10 to 17. Okay, again, this is an 8-bit port. Now this is multifunctional. It can either function as a standard IO port, or it can also provide serial communication. Do you see pin 3.0, pin 3.1, or externally pin 10 and pin 11? This is port 3.0, third port, right? Third port LSB, LSB plus 1, LSB plus 2, LSB plus 3, LSB plus 4, LSB plus 5, LSB plus 6, LSB plus 7. So this is LSB 0th bit. This is MSB the 8th bit. So either P, you can refer to a particular pin as with either its port number, pin 3.0, 3.1, 3.2, or with pin number 10, 11, 12, 13 with related to the chip. Okay, but the notation that I'll be using to explain will be in reference to the port number. Okay, we call this as port number, we call this as pin number. If you look at pin 3.0, it is for receiving. It's the receiving pin for serial communication. And if you look at port port 3.1, it is for transmitting data serially, or otherwise pin 10 is used for serial reception and pin 11 is used for serial transmission. So apart from general IO, port 3 can also act as serial communication when you use these two pins for serial transaction, serial data transaction. Now apart from this, pin port 3.0 also houses two interrupts, INT0, INT1. Okay, INT0 and INT1, that is P3.2 and 3.3. or otherwise pin 12 and pin 13. Now if I come down, you see a read active low signal and a a read active low signal and a write active low signal, P3.6 and 3.7, that is pin 16 and 17. These two are used especially when you want to interface external memory. These two are used whenever you want to interface external memory. So generally, if you look at the functionality of port 3, that is pin 10 to pin 17, it can either act as a general IO or it can house serial communication, or it can house control signals for reading or writing data from or to the external memory, plus interrupts, two external interrupts, INT0, INT1. Now if you decide to use this entire port as IO, you cannot use any of the other functions listed here. If you want to use the other functions listed here, this port cannot be used for general IO operations. Though we say it's multifunctional, at a time only one of the functionality can be used. Okay, now let's come to port 0, which starts from pin 39 all the way till 32. So port 0 is from pin 39 to pin 32. So P0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, again 8 bits. Now this is also multifunctional in the sense this can be either used as general IO pins or ports, or it can be used for placing the lower 8 bits of the address. Okay, lower 8 bits of the address. Where this comes into play, I told you if you want to interface external memory outside 8051, I told you, we'll be using this for reading and writing, right? So where it has to write, where it has to read from. Okay, the address has to be placed in a 16-bit address bus. So this forms the lower 8. Okay, this forms the lower byte of the address. So port 0 can be either GPIO or it can be used for placing the lower bits or a lower byte of the address. Now port 2 is from pin 21 to pin 28 or 2.0 to 2.7. Again, this is an 8-bit port. Now this is again multifunctional in the sense it can be either used as a standard IO, or this can also be used for placing the upper byte or the upper byte of the 16-bit address. So this forms the lower byte of the 16-bit address, and this will form the upper byte of the 16-bit address. So this is how this works as a dual. So in case I am going to interface an external memory, the only port that I can completely use for interacting with the 8051 is port 1. Port 3 will be occupied with this read and write. I cannot use it as a regular 8-bit IO port. Okay, again, if you look at the port 0 or port 2, they will be used for placing the address on the data bit, 8 bits of data and 16 bits of address. So I cannot use it for general IO operation. In case I am not interfacing external memory, I have the liberty to use port 1, port 0, port 2 completely for any IO operation, and port 3, assuming I am not using any serial communication or read-write operation or interrupt-based operation, I am free to use completely port 3 as well. In case I am using any of the other functionalities of port 3, I will be left only with port 1, port 0 and port 2. Okay, is the functionalities of different ports and how to use them clear? Fine. These are the other pins, okay, that I was talking about. 3.0 is used for receiving, serial receive. 3.1 for read and transmit, INT0, INT1, counter, pin 14 and 15, the T0, yeah, I forgot to mention, T0 and T1 is used for counting. In case I want to build a small frequency counter program, if I can connect the incoming wave to this, I can count. This will trigger the counter. Every time the signal changes here from low to high or high to low, I can make it either edge triggered or level triggered, and I can count. Okay, so these are the other pin functionalities. I will give you a couple of seconds to take a look at it and map it to the diagram. Fine. Now this is how the memory structure looks like in an 8051. The memory ranges from 00H all the way till 7FH. So this is the range of 8051. Now, how the memory is divided, there is an element of surprise to you. Whenever you programmed in Kale, you saw a set of general purpose register available for your data manipulation, right? R0 to R7, that is 8 registers, right? But the element of surprise here is there are totally, 4 banks. Bank 0, Bank 1, Bank 2, Bank 3. 4 banks with each containing 8 registers. So ultimately, if you look at 8051, for your data manipulation, you have totally 32 8-bit general purpose registers. But only 8 are available per bank. Only 8 are available per bank. So you have exhausted all these registers. You can shift your bank and use the other registers. Again, you have, okay, there is a typo here. This should be bank 0, bank 1, bank 2, and bank 3. But instead of that, it simply says bank 1, bank 1, bank 1. It's bank 0, 1, 2, and 3. So you can shift between the banks, transfer the data, and still work on these registers. So totally 8 registers, general purpose registers per bank, and you have such 4 banks. So how do you change banks? Remember, in program status word register, you had carry, auxiliary carry, parity, then 2 general purpose flags F0 and F1, and there will be 2 bits called RS0, RS1, or sometimes it's RS0, RS1. If the RS0, RS1 bits are 00, it refers to bank 0. Okay, RS0 and RS1 are 00, it refers to bank 0. If they are 01, it refers to bank 1. If they are 10, it refers to bank 2. If they are 11, it refers to bank 3. So by writing the appropriate number in the RS0 and RS1 bit of the PSW register, you can shift from bank 0 to bank 1 to bank 2 and to bank 3. Okay, irrespective of which bank you are in, the registers are always named as R0 to R7. This will not create any confusion, because if you look at the location of these registers, the location is entirely different. For example, there is a Salem in Tamil Nadu, there is also a Salem in United States. But that doesn't mean it's the same Salem. It can be clearly demarcated because of its totally different location. So similarly, even though there are the registers are named 0 to 7, R0 to R7 in every register bank, since the location are entirely different, the processor will not get confused about it. Okay, so this is the general purpose RAM area, which is of 80 bytes. These are bit addressable memory area. Generally, I told you in memory, it will be always byte, every location is a byte wide. But this particular location in 8051 can be bit addressable, because you can write to every bit, you can read every bit. So bit addressable. Okay. Apart from this, you also have some special memory location for SFR and internal RAM. Internal RAM varies from 0 to 7FH. This is what you are seeing here. And from 80H to FFH is special function registers. It is reserved. That means you cannot simply access or use this particular region of memory. It is for special function register. And this is the area you can play with. That is 00 to 7FH. Okay. So what are some special function registers present in 8051? PCON, power control register. SBUF, serial buffer register. This is used whenever a serial communication happens via port 3. Then this is IP, interrupt priority. There are 6 interrupts in 8051, INT0, INT1. Please refer to the diagram which was shown before. Those are 2 external interrupts. Apart from those 2 external interrupts, you have 2 timer interrupts and 1 serial communication interrupt and 1 reset. Putting all together, you have 6 interrupts. So if you want to, each interrupt has its own priority. So if you want to change the priority of those interrupts, this is the register, IP register, interrupt priority register is where we go. You're familiar with PSW, program status word. This is DPTR, which is a 16-bit register used for data pointing whenever some kind of memory-based access needs to be done, either for reading or writing. This is SCON. SCON is nothing but serial communication control register. This is where you set the baud rate, you tell them what kind of communication is happening. TCON is nothing but timer control. TMOD is nothing but timer mode. I told you there are 2 timers present in 8051, timer 1, timer 2. TMOD is the register through which we can program the timer in various modes. A timer can run as a 16-bit timer, as an 8-bit auto reload timer, split timer. So which mode you want the timer to run. That is controlled by this TMOD register. TL0, TH0 are nothing but registers associated with timer 0. TL1, TH1 are nothing but registers associated with timer 1. We'll see about this in detail in the future slides or lecture. So these are the special function registers available in 8051. The first topic that we are going to deal is about timers, because they have variety of applications and it's very interesting and easy to learn as well. So that's why timers first. As I told you before, 8051 has two timers, timer 0 and timer 1. Okay, the timer can perform three functions. One, keeping time, that is, it can count like your watch, clock. Then counting. Okay, see, the difference between keeping time and counting is, as far as keeping time is concerned, once you initiate, it goes on forever. Okay, whereas counting, it doesn't do automatically. Counting is based on an event that is being triggered. Like I told you, frequency counter is a very good example for counting operation. Then the third functionality is setting the baud rate for serial communication. I don't know how many of you have already worked with serial communication. When two devices of different speed communicate, for example, your 8051 runs from 12 megahertz to 30 megahertz. Let's assume it is running at the maximum speed of 30 megahertz. Say via serial communication, I'm connecting it to your PC. PC is much faster than your 8051. So whenever these two devices are communicating, unless the timing synchronization is there, okay, the communication will not be fruitful. You will be getting only junk data. You will not be getting the proper data. So it's very important to synchronize the time. So baud rate is very important. So timer performs all the three functions: keeping time, counting, and baud rate. I already told you 8051 has two timers, 8052 has three. Now the registers associated with timers are TCON, TMOD, TL, TH. I already told you TCON is for controlling the timer. TMOD is the register through which we program which mode the timer will operate in. TL and TH are associated with the timer 0 and timer 1 respectively. Now of this TCON register, this is the address of the TCON register. This is TMOD register and this is the address of the TMOD register. Both are 8-bit registers. TCON and TMOD are common to both timer 0 as well as timer 1. If you can see here, it is the same TMOD for timer 0 as well as timer 1, and it is the same TCON for timer 0 as well as timer 1. So TCON and TMOD are common. So what is unique? TL and TH. Okay, for timer 0 you have TL0, TH0, and for timer 1 we have TL1, TH1. So these are two separate 8-bit. TL1 is a separate 8-bit register. TH1 is a separate 8-bit register. So is TL0 and TH0. So these are unique to the timer. This is associated only with timer 0. This is associated only with timer 1. Whereas TCON and TMOD are both common to timer 0 as well as timer 1. Got it? So this is the overview of the timer in 8051. Now let's look in detail about TCON register or timer control register. Now if you look at the timer control register or TCON register, I told you it's an 8-bit register. So it's 0, 1, 2, 3, 4, 5, 6, 7. 8 bits. Of that, if you see, the upper 4 bits are used for timer 0, timer 1, and the lower 4 bits are used for controlling the timer. Now what is this upper 4 bit, lower 4 bits? What is TF1, TR1, TF0, TR0, IE1, IT1, IE0, IT0? We are going to see now. TF stands for timer flag. TR stands for timer run. IE stands for interrupt enable. Okay. IT stands for edge triggered or level triggered. Okay, again I'm repeating. TF stands for timer flag, TR stands for timer run. Okay, IE stands for interrupt enable, and IT is for level triggered or edge triggered. The suffix 1, 0 always indicate whether it is associated with timer 0 or timer 1. So if you take the upper 4 bits, okay, If you look at bit number 5 and 6, okay, I'm starting from 0. So if you look at bit number 5 and 6, they are TR0, TF0. So TR0 is associated with timer 0, TF0 is associated with timer 0. TR bit, the timer begins to count, or the timer begins to work like a clock only when this TR bit is set to 1. If you do not set the TR bit to 1, the timer will not initialize. The timer or the counter for that matter will not initialize. So if you want timer 0 to run, you have to set TR0 to 1. Similarly, if you want timer 1 to run, you have to set TR1 to 1. Otherwise, the timer will not start. Now, what is this TF0, TF1? They are timer flags. In case the timer overflows, these flag bits are set automatically. These flag bits are set automatically. In the sense, the user has the flexibility of resetting this timer flag to 0. I can make this from 1 to 0, but I cannot set this flag by myself, or by using some instruction I cannot set this flag. The control is totally with the processor. Whenever a particular timer overflows, you know what you mean by overflow, right? Whenever a particular timer overflows, this flag will be set automatically. Okay, so if I have to resume the timer operation, I have to do two things. What? Before setting this to 1, I have to clear this bit to 0. Okay, and then start the timer. If you start the timer again without resetting this flag, the timer will not initialize, because this, as far as this particular flag is 1, this flag TF0 or TF1 is 1, the timer will not run. Only when this is 0 plus this TR0 or TR1 is set to 1, the timer will run. The moment the timer overflows, this TF flag will be set to 0. Okay, we'll see about that in detail when we program in Kale. So this is the upper 4 bits common to timer 0 and timer 1. What are these lower 4 bits? Okay, see, when you want to run the timer in manual mode, okay, you check whether TF0 has become 1 or not by polling. But if you want to do it in automatic mode, all you have to do is simply enable the interrupt. If you want to enable timer 1 interrupt, set this bit to 1. If you want to enable timer 0 interrupt, set this 1. So what this actually will do is, whenever the flag overflows, there is an interrupt service routine that will automatically clear this flag and set the bit to 1. You don't have to do it manually in your code. It will be done automatically. Now, what is this IT1 and IT0? Whether you want the timer to be sensitive to edge or level triggered. Already I've told you what is edge triggered, what is level triggered while talking about memory read write operation. So recall that. So this IT0 or IT1 will make timer 0 or timer 1 either edge triggered or level triggered. So this is TCON register for you. Next comes the TMOD register. I told you TMOD register is nothing but timer mode register, TMOD. So basically, using this register, we govern on what mode the timer operates. Okay, now let's look at the structure of TMOD register. Again, it's an 8-bit register. Unlike TCON, the lower 4 bits are for timer 0, the upper 4 bits are for timer 1. Again, once again, if you go to TCON register, you can see it's a mix. The upper 4 bits is both for timer 0 as well as timer 1. The lower 4 bit is for both timer 0 and timer 1. So you have a combination here. Whereas TMOD register, it is very clear. The lower 4 bits is for timer 0. The upper 4 bits is for timer 1. Okay, whether it is for timer 0 or timer 1, the functionality is the same. Let's see. Okay, if you look at timer 0, for example, you have 4 bits. What are the 4 bits? M0, M1, C/T, gate. Okay, now what is this M0, M1? This sets the mode. If this is 0, 0, it is mode 0, 0, 1, mode 1, 1, 0, mode 2, 1, 1, mode 3. So what is this mode 0, mode 1, mode 2, mode 3? If you look at the definitions here, if you program it as mode 0, that is write 0 and 0 here, It's called a 13-bit. It will act in a 13-bit timer mode. 13-bit timer mode. That is the maximum count or the maximum timer value it can go is 2 power 13. Okay. Now if I'm going to write a 0, 1, sorry, if I'm going to write 0, 1, 0, 1 here, it's going to act in a 16-bit mode. That is, it can go up till 2 power 16. That is 65536. If I write 1 and a 0 here, it is going to function as a 8-bit auto reload mode. If I'm going to write a 1 and a 1 in the timer mode bits, it's going to act as a split timer. Now what is this C bar T? This is nothing but it is to tell the processor whether we are using the timer in timer mode or counter mode. If this is set, if you write a 1 in this bit, it is set as counter. If this is 0, it is going to act as timer. So that indicates the processor whether the timer is going to be used as a counter or timer. Now what is this gate bit? Remember I told you I was talking about the interrupt. So this gate responds to INT0 or INT1 if set to 1. You got it? Similarly M0, M1, C bar T or gate bit for timer 1. This is to set different modes of the timer. This is to tell the processor whether it is being used as a counter or timer. This is for interrupt purpose. So this is TMOD register for you. So how does timer work, or how does it actually function? When you program a timer, okay, a timer increments for every one instruction cycle. Every one instruction cycle. Why am I emphasizing on instruction cycle? Because clock cycle is different from instruction cycle. Okay, clock cycle and instruction cycle need not be the same always. Sometimes an instruction cycle can also be a clock cycle if that instruction executes in one single clock cycle. Remember in ARM I told you every instruction is a single clock cycle instruction. In that case, instruction cycle and clock cycle are the same. Sometimes the instruction cycle is also called as machine cycle. Whereas in 8051, if you look at, almost every instruction takes 12 clock cycles to execute. So what does that mean? One machine cycle or one instruction cycle is equal to 12 clock cycles. Is equal to 12 clock cycles. So therefore, I told you timer ticks. When I say tick, it's nothing but it is moving. Okay, it is moving. It is moving like this. Tick. This is what we call as one tick. 1 tick, 2 tick, 3 tick, 4 tick, 5 tick, 6 tick. So every time it moves, it's called a tick. So a timer when programmed, I told you, it moves or ticks for every instruction cycle. At the same time, I told you 12 clock cycles are consumed by an instruction. So one instruction cycle is equal to 12 clock cycles. Therefore, if you look at the timer, it can tick up to 920,000 times per second, or in Indian style, if you say 9,21,000 times per second. So per second, the timer in 8051 is capable of ticking 9,21,000 times. Okay, this is assuming the clock frequency as 12 kilohertz. Now, how to actually program the timer to work? Okay, I told you TL register, TH register are associated with the timers, individual timers. If it is timer 0, TL0, TH0. If it is timer 1, TL1, TH1. Okay, so what we do is the TL register will carry the hexadecimal number, okay, up to which it is going to count. For example, if I load FF in TL register, okay, let me go to this. Let us assume that in TL register I am going to load FF. So what's going to happen is the timer will start counting from 0 to FF. Okay, so this is my lower limit and this is my upper limit. So depending upon the delay you want, I can load an appropriate hexadecimal number in TLX TL register, and once you initialize the timer, it will always count from 00 to that number. So what does TH register hold? It holds the multiple. What do I mean by a multiple is, say for example, 00 to FF, it counts once. Suppose that delay is not sufficient for me, but whereas if it counts 5 times 0 to FF, then probably I might get the delay I want. So that multiplier number is loaded onto TH. This is also a hexadecimal number. So TL will contain the upper limit. Okay, so the timer will start counting from 0 to that upper limit number, and TH will contain the multiplier term, which is also a hexadecimal number. So for example, if I write FF in TL register and I write 0A in TH register, what do you think will happen? The timer will count from 0 to FF how many times? 10 times. After counting 10 times, when it goes for the 11th time, it has exceeded its limit, because I have given only number 10 here. So when it goes for the 11th time, the number exceeds and the timer overflows. When the timer overflows, as I was describing earlier to you, the timer flag is set. This is when we have to either clear the timer flag using interrupt, or we have to manually clear the timer flag and again run the timer so that it runs for the second time. You understand the significance of TL and TH? Okay. Now how to calculate the delay? Okay, last slide when I went back, I told you, you have to load a number in TL depending upon the delay you want, and a multiplier number in TH depending upon the delay. So what is this delay? How to calculate this delay? Okay, now I told you TH register is an 8-bit register and TL register is also an 8-bit register. Okay, so what is the maximum count I can go for? Here I can go to 0 to FF. How many times maximum? FF times. So what is the maximum count I can go for? Is FF into FF, or in other words 2 power 16, which is 65536. So that is the maximum count I can go for, right? So how do I calculate the delay required, or the values that should be loaded onto TH and TL is, this is the method, this is a formula. So please listen carefully and understand. So 65536, this is the maximum count I can go for. This is the number that we have to find out, which will be loaded in TL and TH. Multiplied by 1 microsecond is equal to delay time. What is this 1 microsecond? Assuming my clock frequency is 12 megahertz. Okay, I told you 12 clock cycles take one machine. One machine cycle is equal to 12 clock cycles. So that is why I am dividing the clock frequency by 12. So this is 1 megahertz. So if you convert the frequency into time, it will be 1 microsecond. Always this will not be 12 megahertz. I told you the clock frequency can range anywhere from 12 megahertz to 30 megahertz. You get it? So if it is 12 megahertz, it will be 1 microsecond, because 12 clock cycles are consumed by one instruction. That is why this division by 12. This will remain constant, but this will depend upon the clock frequency. In turn, this number will vary depending upon the clock frequency that is being used. Let us see an example, okay, of how to work with the delay calculation, so that we can find the appropriate TL values and TH values in the consecutive video lecture. I welcome you to the next video lecture. In last video lecture, we saw about how to calculate the delay or how to calculate the value that needs to be loaded in the TL register and TH register in order to produce the delay you want in a generalized form. In this particular video lecture, we are going to see an example of how to do it. For example, I want to generate a delay of 5 milliseconds between two operations or between two functions. The delay I want is 5 milliseconds. So how to calculate what value should be loaded in TH and TL and TH registers. As I told you before, 65536 because that's the maximum count I can go for. TL is 8-bit, TH is 8-bit, totally 16-bit, so 2 power 16 is 65536. This X unknown value represents the hex value that I have to load in TL and TH register. So 65536 minus X into 1 microsecond. I told you again how 1 microsecond occurs. I'll let you know again how that is done. Okay, I am assuming a clock frequency of 12 megahertz. Again, I am assuming the clock frequency. While in exam, if the clock frequency is given, you have to take that particular clock frequency into consideration for calculation. In case it is not given, you have to write your assumption. If you don't write your assumption, I can assume any value and I can say you would have assumed 12 megahertz, I would have taken it to 30 megahertz and I would mark your answer as wrong. So if you assume anything, please directly put it in paper. If it is explicitly given, use that value. So in this scenario, I am assuming the clock frequency of 12 megahertz. As I told you already, 12 clock cycles are consumed by one instruction. This is just the continuation of what I said in the last video lecture. So that means 12 clock cycles is equal to one machine cycle or one instruction cycle. So I don't want to go in terms of clock cycle, I want to go in terms of instruction cycle because the timer ticks for every instruction cycle or machine cycle. So I am dividing this by 12. So what do I get? 1 megahertz. So convert it to time, I'll get 1 microsecond. Now if the clock frequency is 30 megahertz, what will happen? So this will be 30 megahertz divided by 12 and you have to convert whatever answer you get in frequency into appropriate time and then multiply it here. Okay, so in this case I am assuming 12 megahertz. Okay, so it's 1 microsecond. So 65536 minus X into 1 microsecond is equal to 5 milliseconds. So that is nothing but 5 into 10 to the power of minus 3. So when this multiplication goes to the other end, it becomes division, right? So it will be 5 into 10 to the power of minus 3 divided by 1 microsecond. Micro is 1 into 10 to the power of minus 6. So when this goes up, it is 5 into 10 to the power of minus 3 into 10 to the power of 6. This is nothing but 5 into 10 to the power of 3 or 5000. So that is what is written here. Okay, so 65536 minus X is equal to 5000. Or what is X equal to? Take this X on the other side, bring the 5000 on this side. 65536 minus 5000 is equal to X. Now this is decimal. This is decimal. So I told you TL and TH will have hexadecimal number. So convert this decimal number into hexadecimal. So when you convert the decimal, you will get 4 hexadecimal numbers. Okay, so I'll call it H0, H1, H2, H3. So when this difference, which is a decimal number, is converted to hexadecimal number, I'll get 4 hexadecimal numbers. The lower two numbers go to TL register and the upper two numbers go to TH registers. Again, I'm repeating this calculation for you people to understand. If I want a delay of 5 milliseconds between two functions or operations, how do I calculate what value should be loaded in TL register and TH register? Very simple, 65536 minus X. This is the maximum count. X is nothing but the value that needs to be loaded in TH and TL into 1 microsecond. I told you how I got 1 microsecond is equal to the actual delay 5 milliseconds. Okay, now when this 1 microsecond goes to the other side, so it will be 5 millisecond divided by 1 microsecond. So that is the calculation I have shown here. 5 milliseconds divided by 1 microsecond. Milli is nothing but 10 to the power of minus 3. Micro is nothing but 10 to the power of minus 6. So this, when goes up, will become 10 to the power of 6. So this is 10 to the power of minus 3. This is 10 to the power of 6. Eventually the result will be 10 to the power of 3. So that is nothing but 5 into 10 to the power of 3. That is nothing but 5000. So that's how I got this value 5000. So 65536 minus X is equal to 5000. I want to find what is the value of X. So take this X to the other side, bring this 5000 to this side. So 65536 minus 5000 will give me X. But this value cannot be directly loaded onto TH and TL because that is a decimal value. So convert the X, which is decimal, to hexadecimal. And the lower two digits are loaded onto TL register and the upper two digits are loaded onto the TH register, and this is how I calculate the values to be loaded on TL and TH so that I get the appropriate delay. So for example, based on this calculation, for a 5 millisecond delay, what I need, okay, the values that I came up with are 0533H. After converting the decimal value to hexadecimal, I got 0533H. So this will go to TL register. So this will be written to TH register. So what does this indicate? The timer will count from 0 to 33H. How many times? 5 times. That is what this indicates. So how do I know, how do I move these values to the respective registers? Very simple. I'll talk about this, I'm going to operate as 16-bit register. So if you go to TMOD, what I have explained earlier, if you write 10H, what does this 10H mean? So it is 0 0 0 1 0 0 0 0. So this is nothing but 1, this is nothing but 0, so this is 10H. So place the bits appropriately in the TMOD register and find out in what mode I am operating and which timer am I operating. Is it timer 1 or timer 0? Timer 0 remains untouched, so I am using timer 1, or whatever, find out what values are supposed to be written. So move TL 33H, move TH 05H. So I have moved the appropriate numbers in TL and TH. Let us not bother whether it is timer 0 or timer 1 because it doesn't matter. Now I told you TR. Remember, while talking about the registers associated with timer, we spoke about TR1, TR0 and everything. Okay, this is a typo error. This should be 1. This is TL1, TH1, not TL0, TH0. This is a typo error, so please correct it because I am using timer 1. Even if you expand this, timer 1 is being used, timer 0 is not being used. So TL1 33H, move TH1 05H, set B TR1. I told you this is for timer run. Timer run. Okay, so unless this is set to 1, the timer will not initialize. So I have to use the command set B. What does set B indicate? Set bit, because this is a bit operation. TR1 is a bit, not a byte. So set bit, set B TR1. So this sets the timer run bit to 1, after which, after this is executed, the timer will start running continuously till it overflows. In this case, I am not reinitializing the timer, so it will run one time and then stop. You get it? How to make the timer work. Now try a small program. Okay, try to generate a timer delay of 2 milliseconds. Remember, in one of the Kale video lectures, I told you how to generate delay by just using registers and D, J, and Z. Now that is more of a crude delay that you can generate. Timers are known for generating very appropriate or very accurate, perfect delay. Okay, this is very useful in square wave generation. So how will you generate square wave using this timer and this delay combination? Very simple. This is 1, this is 0. 1 stays on for this time. So what you do is you write 1 to a particular port, then have the delay where the 1 remains as 1. After the delay, you clear it to 0, so it will remain here, it will go here. Again run the same delay, so the 0 will remain 0 for that many delay, the value will not change. Again after the delay, you change it to 1. Again after the delay, you change it to 0. So ultimately, if you connect it to a CRO or look at the simulator window, you will get a square wave. You get it? So these are the ports, their address associated with each port, and I told you they are 8 bits, right? So just take a glimpse so that you can understand what is what. Port 0, port 1, port 2 and port 3, all the 4 ports, their address associated and the bit address of each pin in the port. Okay, so how to declare a port as input, how to declare a port as output, how to write a value to the port, how to read a value from the port is what we are going to see now. So in order to configure a port as input, we have to write FF to it. In order to configure a port as input, we have to write FF to it. In order to configure a port as output, you have to write 00 to it. Simply remember like this, 0 is looking like output O. So whenever you have to configure a port as output, write 00. Whenever you have to configure an port as input, you write FF. So how do you do that? Very simple. What you do is move A, 0 FFH. Whenever you are writing an hexadecimal number, please always add a prefix of 0. If you don't add 0, this will be considered as an alphabet or a string and it will give you an error. So to avoid it, whenever you are writing a hexadecimal number, always add a prefix as 0. So move A, 0 FFH and move A, to P0. This P0 is nothing but the entire port. Now P0 is configured as input port. Okay, after this has been configured as input port, how to read from the input port? Simply say move P0, A. Simply say move P0, A. And you can either save it in some other register, or if you want to output it as through some other port, you simply say A, P1. P1, P0, all these ports can be treated like any other register move operation. Understood? Got it? So this is how you configure a port as input and you read from it and you write to a different port. Similarly, if you want to configure a port as output port, simple, I already told you, 0. Move 0 to the accumulator, then from accumulator move it to the port. As simple as that. Okay, this particular routine is nothing but a simple program which toggles a particular port. Quite often. Okay, understood? Good. In the next video lecture, we will talk about how to write or configure timer using Kale, how to generate square wave using Kale. And in the following video lectures after that, we'll talk about the interrupt concepts, serial communication concepts in 8051. Thank you.